Have you ever wondered why a movie recommendation might feel off, or why a product suggestion seems unrelated to your interests? The answer lies in a hidden challenge that even the most advanced recommendation systems face: confounding. It's a tricky problem that distorts how AI learns from data, and it's hiding in plain sight. Let's start with a simple but powerful concept: correlation isn't causation. Imagine a study showing that people who drink more champagne live longer. At first glance, it seems like champagne is the secret to longevity. But here's the twist: what if income is the real hero? Wealthier individuals can afford both champagne and better healthcare, which explains the longer lifespans. This is Simpson's paradox, a classic example of confounding, when an unmeasured factor, like income, distorts the relationship between two variables: champagne consumption and life expectancy. Now picture a recommendation system. You might think we've got all the data. There's no hidden factor messing this up, but here's the catch. Many standard practices in these systems accidentally ignore critical information. When that happens, confounding sneaks in, skewing results and making recommendations less accurate. Let's break it down. Recommender systems use features, like browsing history or past purchases, to personalize suggestions. But what if a system drops a key feature, say your location, because it's labeled noisy or unimportant? That's like ignoring income in our champagne example. The model might think a product is popular because users click on it, but the real reason could be something else entirely, like your location influencing both your browsing habits and the products available to you. The paper we're exploring dives into how this happens. For instance, feature engineering, a common practice where engineers tweak data to improve models, can accidentally remove critical variables. Or A/B testing, where changes are tested on small groups, might not account for hidden biases. Even modularization, breaking systems into smaller parts, can create blind spots. Here's the kicker: when a system uses a feature like location but doesn't properly account for it, it's like leaving a door open for confounding. The model might think a product is popular because users click on it, but the real reason could be something else entirely. The research shows that fixing this isn't just about adding more data. It's about rethinking how we design these systems. For example, when introducing new features, we need to ensure they're properly integrated into the model's logic, not just tacked on. And when testing changes, we must check if hidden factors are still messing with the results. So next time you get a weird recommendation, remember, it might not be the algorithm's fault. It could be a hidden factor, like location, income, or even time of day, distorting the data in ways we don't always see. Imagine you're building a system that suggests videos based on what you watch. You train it using past data. People who watch this also like that. But here's the catch: what if the data is biased? For example, maybe the system only sees clicks from users who already like action movies. It starts thinking all users prefer action, even if that's not true. That's confounding, when hidden factors distort the model's understanding of what's really important. In the research we're looking at, teams tried to fix this by splitting their models into parts, like a click model and a purchase model. But here's the twist: when these models are trained separately, they can ignore important clues. Think of it like two chefs cooking different dishes from the same ingredients, but using different recipes. One might focus on flavor, the other on presentation, but neither sees the whole picture. The result? Their recommendations clash, and the final dish, the system's output, is worse than it could be. The study shows this problem in action. On day 3, a recommendation system CTR, click-through rate, plummets because it's relying on flawed data. But by day 4 and 5, things stabilize, only because the model forgets the bad data. It's like a student who studies from a biased textbook. They might fail a test, but after switching to a better source, they improve. The catch? Waiting isn't always an option. So how do you fix this? The research suggests a few key ideas. First, when testing new recommendation strategies, like A/B testing, make sure each model learns from its own data, not a shared pool. It's like giving each chef their own recipe book, instead of letting them copy from each other. Second, be cautious when adding or removing features from your models. A single change can ripple through the system, creating new biases. And finally, consider using balancing scores, a fancy way of saying, focus on the factors that truly matter instead of getting lost in the noise. The takeaway: confounding isn't just a technical glitch. It's a hidden force shaping the recommendations we see every day. Whether you're a developer or just a user, understanding this problem helps us build better systems. After all, even the smartest algorithms can get confused if the data isn't structured properly. Ever wondered why some experiments don't always give clear answers? Let's dive into a tricky problem called confounding, and how it messes with even the smartest AI models. So imagine two models. Let's call them Model A and Model B. They're both trained on the same data, but here's the catch: when they're combined, something weird happens. Confounding. This is like when two factors in an experiment are tangled up, making it hard to tell which one is actually causing the result. The research shows that when these models share data, this confusion sticks around as long as the test is running. It's like a ghost in the data that won't go away. Now picture this: there's a graph showing two approaches to A/B testing. One uses separate data, blue, and the other mixes everything together, red. The key takeaway: only the group trained on combined data, population A, suffers from this confounding. Why? Because when models see overlapping information, they start influencing each other in ways that skew results. Here S where it gets really interesting. The study includes a causal graph, figure 4, that breaks it down. Think of it like a map of relationships. The sale model only sees one part of the data X, while the click model only sees another part X. But because they're connected, they end up confounding each other, like two puzzle pieces that don't fit, but somehow still affect the final picture. So what does this mean for real-world AI? If we're not careful, combining data can create misleading patterns that make our models think they're learning something useful, when really, they're just chasing shadows. The takeaway: always check how your data is structured, because even the smartest algorithms can get confused if the pieces don't fit. Want to see how this plays out in practice? Let's explore the next part of the study,